By the end of this video lecture series, students will be able to differentiate between amorphous and crystalline solids, and they'll be able to explain the structural and bonding characteristics of ionic, metallic, molecular, and covalent network solids. So there's going to be two main characteristics that a solid falls into. The first one is going to be amorphous solids, and those solids are going to have a fair amount of disorder, meaning that their structure is not super organized or repetitive in terms of its organization pattern amongst its atoms. So something like we see here to the right. So examples of amorphous solids are going to be like glasses or plastics. And one of the main characteristics associated with these types of solids are going to be changes in things like melting point. So the melting point for the amorphous solids is actually going to occur over a range. Okay, so the fact that there isn't a consistent organized pattern that is present in this molecule makes it where, certain areas of the sample may have slightly different intermolecular or intramolecular forces, and that subsequently might lead to differences in the energy required to separate out those atoms. Okay, and so this is what leads to the range that we see in terms of the melting point of an amorphous solid. Now, a crystalline solid is going to be much, much more organized. So as we can see here, we have a repeating pattern, very structured, very organized. Okay, and this is the most common way that you'll see solids organized in nature. So what ends up happening here is this regular arrangement leads to basically a melting point that actually occurs at a specific point. Okay, so because of the organization and the consistency within the lattice structure, within the organization pattern in the solid, you're going to have a specific melting point for the crystalline solids, while you're going to have a range with the amorphous. So different types of crystalline solids that we're going to be looking at today. So the four that we're going to be looking at are ionic solids, which are characterized by electrostatic interactions between ions. We're going to be looking at metallic solids, which are represented by a sea of electrons. We're going to look at covalent network solids, which basically are represented by atoms that are covalently bonded across an array. Okay, and we're going to look at molecular solids, which are formed through the intermolecular forces between atoms. So we've talked about ionic solids in pretty good detail. We know that ionic solids are held together by the electrostatic interactions between positively charged cations and negatively charged anions, as seen here in the diagram below. Now, we know also, according to Coulomb's law, that the larger the charge and the smaller the size of the ions are going to lead to greater attractive forces, and that attractive force is going to be directly connected to the additive aspect of the lattice energy. And basically high lattice energies lead to very high melting points, and basically some of the features that we expect with ionic solids. So again, ionic compounds are good insulators. They're brittle. They're brittle because any disturbance between the ions in the lattice are going to lead to repulsive forces, and we see that here. Okay, so we have positives and negatives in close proximity in the lattice. If we move this portion of the lattice down one atom, basically what ends up happening is the positively charged ions will be in close proximity, and that's going to lead to repulsive forces. And so basically that's why they crumble pretty easily. So we're pretty comfortable with ionic solids, so let's go ahead and move on. So metallic solids basically are characterized by the electron C model. We could also look at it with respect to molecular orbital theory, but that's outside of the focus of this class. So the electron C model basically just says that we have metal ions, okay, that are basically free floating within a sea of delocalized electrons. So delocalized means that the electrons are not in a specific area. They move randomly throughout this structure. Okay, so and these free-floating or delocalized electrons contribute to a lot of the features associated with metallic solids. Okay, the ability to conduct electricity and heat. So the electrons, when we apply electrical current, basically the electrons don't have a problem moving on through the metal because basically the electrons are just floating randomly anyway. Heat works in that same way. Basically, these delocalized electrons allow that heat energy to be transferred through in a very easy way. Okay, the malleability and ductile features of metals, their ability to be shaped or drawn into wires, is also basically predicated on the idea that the electron C model allows the electrons to just reorient themselves. Okay, so if we, hammer on the metal or pull on it, basically the metal ions and electrons are just going to reorient themselves and still stay connected, but basically get drawn into whatever shape we desire. So molecular solids are going to be characterized by strong intramolecular forces that actually hold the atoms in the molecules together. But the actual solid is going to be formed by the intermolecular interactions between molecules. So the bonding that is actually causing the formation of these solids are the intermolecular forces that occur between molecules. And we've talked about the intermolecular forces in great detail. We have London dispersion forces, which are sometimes called van der Waals, which are the weakest. We then have dipole-dipole, okay, which occur in polar molecules. We then have H bonding, which remember is a special type of dipole-dipole, and a little bit stronger. And then, of course, ion-dipole interactions. So these intermolecular forces, depending on the strength, that's going to dictate the other characteristics of the solid, such as like melting point. The stronger the intermolecular forces, obviously you're going to have to put more energy in to separate out the molecules. So something to mention is that shape of molecules. Again, remember the shape of your molecule is going to dictate the overlap or the proximity that the molecules can have to one another. And so what's going to end up happening is your shape can also affect the ability of the intermolecular forces to form. So we want to make sure we apply all those thought patterns to our molecular solids when we're identifying them. So covalent network solids are actually solids that we haven't discussed before. And basically, covalent network solids are unique in that the atoms within the solid are covalently bonded together in a repeating three-dimensional array. So what ends up happening is you're going to have basically a repeating bonding pattern, covalent bonding pattern throughout the three dimensions of the solid. Okay, and what ends up happening here is because there are so many covalent bonds across the entire structure, what ends up happening is lots of energy has to be put in order to break those bonds, and they typically are very structurally hard. So covalent network solids are known, and you interact with them quite regularly. Graphite or pencil lead is an example of a covalent network solid, and diamond is also an example of a covalent network solid. Now, we can see their diagrams here. And what you see here is that they're both made out of carbon. So diamond and graphite are known as allotropes, which means that basically they're made out of the same atoms, but they have different organization patterns in their crystal structure. So what you notice here is that for the diamond, the atoms are tetrahedrally bonded to one another, and so that gives the specific features associated with diamond, such as hardness and high melting point and things of that sort. Graphite, notice they are covalently bonded in a planar way, okay, in these sheets basically. Okay, and what ends up happening here is that these sheets are pretty hard. However, the sheets do not interconnect top to bottom here. And what ends up happening is these sheets are actually interacting by intermolecular forces. And so that's what allows the graphite in your pencil to slough off onto the paper that you're writing on. Why? Because basically you're wiping away layers of the graphite and placing them onto your paper. So types of atoms and compounds that will bond in this manner. So silicon and germanium, of course. Quartz is an example of a covalent network solid. Silicon carbide and boron nitride. You want to make sure you memorize these and are able to identify them when they come up in questions. So basically the repeating units and that three-dimensional array of bonding, that's what's going to be characteristic of covalent network solids. So let's go ahead and let's identify basically the type of solid that we have, or what kind of solid, will be formed from the various compounds or atoms seen here. Okay, so in this first situation, we have sodium chloride, so NaCl. We know that this is an ionic compound. Okay, so it's going to be an ionic solid. It's pretty straightforward. Okay, all right, HCl has a covalent bond, okay, between it. However, hydrogen is not going to go on and bond to other atoms covalently, right? It can only form a single covalent bond, so we know for sure that this is going to be a molecular solid. And molecular solids form from intermolecular forces, and the types of intermolecular forces that are causing the formation of this molecular solid are the dipole-dipole interactions that occur because that's a polar molecule. Okay, Cl2, okay, it is a molecule with covalent bonds. It's not, carbon, it's not silicon, it's not germanium, it's not some of the ones that we talked about in terms of the covalent network solids, so we know that this is just going to form a molecular solid. Okay, and the intermolecular forces that are going to cause the formation of the molecular solid here are the London dispersion forces. Okay, here we have an atom of zinc. Okay, so if we have this in a repeating array of solids, okay, it's going to be metallic. The reason why I know it's metallic is because zinc is a metal. So that's the kind of bonding or kind of solid that will be created. Okay, and if we come down here, we have an individual element. We have silicon. Okay, silicon's one of the atoms that we know, or the types of atoms that are involved potentially in covalent network solids. So we're going to indicate that this is a covalent network solid. Okay, and basically this is how you'd be identifying each of your substances. Okay, we do want to know and be able to identify, features associated with these different substances. So, ionic solids, they occur in lattices, they have, high melting points, they're brittle. Okay, why are those the case? We should think those through. Molecular solids typically have low boiling points, low melting points. And basically we can look at these and compare molecular solids. I could ask you, which one of these is more likely to melt at a lower temperature. Okay, and of course you're going to say the Cl2, and the reason why is because in order to break up the molecular solid, you need to break up the London dispersion forces. Okay, and that's a weaker force, or that's a weaker intermolecular force than the dipole-dipole interactions. So you would subsequently say that that's the case. Okay, metallic solids, they're represented by a sea of electrons. We know that they're malleable, they're able to conduct electricity. These are all features you would anticipate. And then covalent network solids, okay, obviously they're going to be really hard for the most part, at least relative to other covalent compounds, which, a lot of times are liquids or softer solids. Okay, and, basically they differ drastically when compared to other covalently bonded molecules. So these are just some things to think about when we're looking at solids. Make sure that you're comfortable with each definition and the details associated with each.